hydriodic acid is number 2 on the list there. You look. It goes perchloric, hydroidic. Those are 6 of the 7 strong acids. There's one strong acid missing off that chart. Do you know which one's missing? Yeah, what's the name of that one?
Is it hydrochloric acid?
No.
Oh no, chloric acid?
Yeah, chloric acid's missing. Oh, this one has all 7. Hydroiodic is a very strong acid. Here's chloric acid. Chloric acid's missing off that chart there on the wall. If it's not one of those 7, and you have to memorize these 7, just like the other stuff, with whatever technique you can use to memorize it. But the 7 common strong acids need to be. The reason is otherwise you're not going to know. The only way you can tell if the acid's strong or weak is if it's not one of the 7 strong ones, then it's weak. And then it would be a weak one, right? And so we could go back to this thing here. HI is a strong acid. Strong acids are strong electrolytes. So this would be strong. What is this called?
Rubidium sulfate.
Yeah. And is it strong, weak, or non? So this is a group 1. Rubidium is group 1. All group 1 salts are soluble. So this is a soluble salt, therefore it's strong. HNO2 is called nitrous acid. Nitrous acid, is it one of the 7 strong acids? No, therefore it's weak. Weak acid is a weak electrolyte. HCN, what's this called? Hydrocyanic acid is the name of the acid, or hydrogen cyanide is a gas. Hydrogen cyanide has a history as being a poisonous gas. California, they used to have the gas chamber. Have you heard of the gas chamber? Capital punishment. Like a San Quentin prison or something, they have a gas chamber there, and the gas they used is hydrogen cyanide, or hydrocyanic acid. Cyanide is like carbon monoxide. You know, cyanide binds to your hemoglobin, hemoglobin prevents oxygen from binding. So cyanide and carbon monoxide are similar in there. So lots of people die naturally from carbon, well, not naturally, accidentally from carbon monoxide poisoning. But you could do the same with hydrogen cyanide. And it has an odor to it. It's supposed to smell like burnt almonds. So if you smell something that smells like burnt almonds, then probably get away from that, because it could be hydrogen cyanide. What's this called?
Sodium chloride. Sodium carbonate?
Sodium carbonate is correct. All group 1 salts are soluble, so strong. This
So
one,
like the cyanide, was that strong? Or?
no, is that a strong acid? Is that one of the 7 strong acids?
Oh, no.
No, so therefore it's weak, yeah. Sodium carbonate is a soluble salt. Soluble salts are strong. Ammonia, you have to memorize this one. Ammonia is a weak, this is from yesterday. Ammonia is a weak,
Base.
it's a weak base. Remember it conducted electricity? It wasn't so bright, but aqueous ammonia did. So it's a weak electrolyte, it's a weak base. Weak bases we'll talk about today. What's this called?
Potassium manganate.
Potassium permanganate. It's good. All potassium salts are soluble, so it's strong. Chlorides, bromides, and iodides are all soluble except for 3. Which 3?
Except for silver, mercury, and lead.
Yeah, silver, lead 2, mercury 1. And so this is not one of the exceptions. This is soluble salt, strong. This one, CH3CH2OH, do you recognize that formula? This one's called I wrote it a number of times in class. I don't know how many times, a bunch of times in class. It didn't register, or it's hard to remember. It's hard to remember things unless there's some repetition. So this is why I recommend the repetition, over and over again. You might recognize it. Maybe a guess. The name of that? Nobody? What's wrong with this computer? Should have downloaded it. Obscure things, usually when people think about obscure things, they think, oh, it's not going to be on the test, but you never know. I don't usually put obscure things, but I've been hit with obscure things when I've taken tests. That you either know or you don't know.
Ethanol.
Ethanol, good. But you want a little bit more rapid, Even though ethanol is not one of your nomenclature, the thing is, if it's not in the book and it's not in the homework, then it's not fair, right? But, a lot of people don't care if it's fair or not fair. If you see, it's kind of, it's kind of a cutthroat because there's a lot of people vying for the top score. And so it can be cutthroat a bit. And so they're going to be people who are on it, and they'll surprise you because, wow, why are they doing that?
So for ethanol, can it be written in 2 ways?
No, more than 2 ways.
Okay, because
In the lab it was written differently. And
Yeah,
so
so-
if you were accustomed to the way I wrote it, then you would have seen in the lab it was totally different.
Yeah.
But those are 2 different ways of writing ethanol. They're even more. The way I write it is called a condensed structural formula. The way it was written in the lab was had less information in it, in the formula. What happened to all my things? Weird.
So that would be considered weak, right?
No,
Strong?
no,
Oh, it's a non-electrolyte?
yeah.
Okay.
If it's weak, then what, it has to be a weak acid. Is ethanol a
that's
weak
right.
acid?
No,
No. Is it a weak base?
no,
No. Is it a soluble salt?
no.
Or no, heavy metal salt? Soluble salts are strong. It's not a strong acid, it's not a strong base, it's not a soluble salt. And so out of the process of elimination, it is a, oh, I'm still logged in. Oh, no, I'm not. It is a
Non-electrolyte.
non-electrolyte. It's just process of elimination. That's it. I'm gonna bring up those things I was looking at earlier. So how, you know, how is it best to remember this obscure information? And I'll tell you, the number one thing that made a difference, for me at UCLA was daily review of the notes. As long as you had the information, if you didn't have the information in your notes, then there's no way, you know. That made the biggest difference. And so, and then it's easy to memorize even if you have a poor memory. I have a poor memory, but it was easy to memorize because it was a day-to-day routine. Memorization was always very tough for me. But unfortunately, you have to memorize some stuff for this class. Nomenclature. There are people who try to get by without memorizing any nomenclature. Yeah, but you know, usually by the time, maybe they make it through Chem 4, but by the time they get to Chem 1A, it's likely they aren't going to make it. If they are, you know, they can, if they just blow off the entire nomenclature and then just work on the other stuff, and they can get A's on the other stuff, and maybe not, because you never know, you know, how the instructor is going to weight things.
So for Chem 1A, you would say, we have to go in, with all that stuff memorized, or are they going to?
No, in Chem 1A, they're going to go through it again, of course. So it helps, you know, the repetition helps. So in Chem 1A, it's just more of the same, but it's just harder, more in depth. And so you'll go through it again. So then Chem 1B, you use it. The more you use it, you know, the easier it is to remember the stuff. If you just see it once and never use it again, then it's hard. So a lot of people see it once, and then when they review for the exam, then that's when they look at it again, and it's too late. This is what I used to do. I used to do cram sessions like for the test. And so I try to cram it into my short-term memory. It happens, you know, there's too much stuff, too much volume of stuff to memorize. And so I used to do this, and I'm sure a lot of you do this as well. When you get the test, all that stuff in your short-term memory, you just dump and write it all on the exam before you do anything. You know, so you do a memory dump, and then you can clear your mind. You know. I used to do that all the time, but when I started reviewing every day, I didn't have to do that. In fact, the stress level went from very high to very low. You know, because I had reviewed it so many times. You want to maybe consider, but you know, everybody's unique in the sense that you know, what works for me may not work for you at all. So sometimes you have to just look for something that works. So dig down. Let's see if I can show you that. So ethanol is a non-electrolyte, so just N. What is this?
Strontium hydroxide.
Strontium hydroxide. Hydroxides are all insoluble except for
Except for group 1, ammonium ion, yeah, calcium ion, strontium ion, and barium.
yeah, good. Group 1, ammonium, and calcium, strontium, barium. So that means strontium hydroxide is a soluble salt. It's a soluble salt, we say, strong. This one's easy because all ammonium salts are soluble or insoluble?
Insoluble.
Soluble.
Soluble. And all nitrate salts are?
Soluble.
Yeah. So this one is a soluble salt, which means?
Strong electrolyte.
And so it's going to be, yeah. These are a bit tricky though, because they have a step 2 to them. So in step 1, it's a soluble salt, so the ions break apart from each other. In step 2, the ions themselves can be acids or bases. We've had acid anions, but it doesn't even have to be an acid anion. So for example, when strontium and hydroxide, because this forms what type of structure? Is that molecular or ionic? It's ionic, so it's going to form an ionic lattice. So as water molecules come and pull apart the ions, the hydroxide ions themselves are what we call a strong base. And so that's a strong base. But strontium hydroxide we call a soluble salt. Ammonium nitrate is a soluble salt, but ammonium ions, ammonia is a base. Ammonium ions are an acid. They're not one of the 7 strong acids, but they're an acid. And so just the ion itself, okay. And these are the 7 common strong acids here. Everything else is weak. This is a polyatomic cation that you just have to memorize. It's hydronium. Do you know how hydronium's formed? And why it's formed?
Maybe water gets an extra hydrogen for some reason.
Well, it does, but not for some reason, for a very specific reason. What's another name for H+? Did you guys catch this?
Proton.
Hydrogen ion is one name. What's another name?
Hydrogen proton.
A proton. A proton, why do they call it a proton?
Because it's just one proton.
This is because this is one proton. How big is a proton?
Really small.
Did I talk about this yesterday?
Yeah.
Okay. Yeah, it's really small, which means its Coulombic forces are going to be huge. I mean, it's 10,000 times smaller than a hydrogen atom. And therefore, since it's so reactive, electrically, coulombically, it attacks water, forms hydronium, H3O+. And so you have to memorize this one. This one's special because you don't buy this. Like, you don't go and buy, I'll buy some hydronium chloride. Hydronium chloride, oh, not again. Oh, okay, it's still there. You don't go out and buy it. It forms when the acid loses hydrogen. When these acids lose hydrogen, then we form hydronium because hydrogen ions are so unstable. But regardless, it's a hassle to write hydronium. And so when I write the acid inventory, I always write H+. I don't write H3O+. Some instructors will make you write H3O+. In Chem 1B, we always write H3O+, but this is not Chem 1B. Chem 1B.
So it forms when the acid loses what?
When the acid loses H+, the H+ isn't so stable. It's very reactive in the presence of water. Water is a very interesting chemical. Water can either be an oxidizer or it can be a reducer. It's not so good either way. But water can also be an acid. That is, it could lose hydrogen, or it could be a base.
strong, weak, or I?
Oh, what's going on with this? Somebody know?
So what is it called when something is very reactive because of its small size?
Small size?
Yeah, like H+.
It depends on what? Small size and charge? Small size and charge would be very reactive electrically, you know. So it's like this. In physics, you learn about, you know, if you have let's say if you have a voltage and you spread the voltage out over a large area, then it becomes less reactive. But if you concentrate the voltage onto a pinpoint, then it becomes very reactive. And so that's just concentrating the charge. When you concentrate the charge, things become more electrically reactive, more coulombically reactive. And so this is why well, but when we're looking at this, I don't know if anybody remembers this. Do you remember what I said about size? On the right side of the periodic table, smaller is better or bigger is better, being more reactive? Smaller is more reactive or bigger is more reactive?
Smaller.
Smaller is more reactive on the right side. On the left side of the periodic table, bigger is more reactive. Why? See, this would be like, okay, the first step is just to remember it, you know, and so you just kind of memorize it, and then, you know, after you read it, like, let's say you're reading through your notes, you're reading it every day, and you see, okay, why is that? Pretty soon you start thinking, why is that, right? I did mention it, but maybe briefly, I didn't write it on the board.
On the left side, they're more reactive when they're bigger because, like, on the left side, they all don't have very many electrons in their outer shell, but as you go down, they get larger, they gain, like, a lot more protons. So, like, the positive charge in the center is a lot more concentrated, and stronger, and then the, like, outer shell is smaller.
Okay, that's, you know, it's good to start thinking in that kind of term, you know, the electrons and stuff. But let me take it back, because on the left side, do they lose electrons or do they gain electrons? If they lose electrons, then having more protons, isn't that detrimental to losing an electron? Electron's negative, protons are positive, so if you have more protons, then you'll have stronger Coulombic attraction, which means the electron is harder to lose. And so but it's on the right track, because if you have more protons, you're gonna have more what we call shells of electrons. It's just gonna be bigger. The bigger the atom is, the further away that electron is from the proton. The further away it gets, you know, from the safety of its home, let's say, the easier it is to lose. And so Coulomb's law depends on the inverse of the distance. And it's not just the inverse of the distance, it's the inverse of the distance squared. So as the distance goes out, the attraction drops off exponentially, you know, but that's physics. What we want to know is just, you know, the bigger it is, the easier it is to pluck a proton off, because if it has lots of, not a proton, electron off. If it has lots of electrons, then if it misses one, maybe it's not as detrimental as if it had just a few electrons and you pluck one off, you know. Although it's tricky because, you know, we're looking at different, there's different factors that influence that kind of stuff. But those are the things, like, first you just memorize it, and you don't really care. I never cared, you know. I never cared, did it make sense? I didn't care if it made sense or didn't make sense. You know, for some people, they're hung up like, okay, it's got to make sense. If I don't understand it, then I'm not going to bother memorizing it. And don't get hung up like that, because the first step is to memorize it, and then when you go through it over and over again, then it clicks, like because your neurons are making those interconnections, and eventually something will click, and then it makes sense. But initially it might not make sense, but it's very beneficial to memorize it, because that's developing all those, you got the neuron for that, and then it's developing interconnections and pathways between those. Mm-hmm.
How can an anion behave like an acid?
How can an anion behave as an acid? If it has a hydrogen on there. And so let's take a look at a very common one, bicarbonate. The way we define an acid is an acid can supply H+. Is this a strong acid, weak acid, or neither? Well, it is an acid because it begins with H, but it's a weak acid. And so what we expect is this is going to be quite uphill to form some additional H+ and carbonate ion. It's quite uphill. Now, the H+ here, it can react with different things. It can react with water. But if there's a better, what we call base than water, then the better base is going to attack it. And so if we have a better base present, like hydroxide, the hydroxide is a great base. And the hydroxide loves hydrogen ion because you know what it forms? It forms water. And so this is it. Even though this is uphill, we form a little bit of this, and that hydroxide will immediately attack it. But hydroxide is so strong, it'll attack bicarbonate, even though they both have negative charges. If there's a collision between these two, then hydroxide's going to they're going to get in a tug of war. And so when hydroxide gets in a tug of war with bicarbonate for that hydrogen, even though carbonate's 2-, it has to do with the size. Carbonate's a 2-, but it's kind of a big ion, whereas hydroxide is quite small. And so this is more concentrated negative charge. And therefore, who's going to win this tug of war? Hydroxide. Even though you think bicarbonate because of the 2-, but we have to think a little more than that. And so hydroxide wins the tug of war. And this is why it's an acid, and carbonate ends up losing for the hydrogen ion. So bicarbonate is called an acid anion.
Why was bicarbonate did they use the bi prefix instead of the di?
Di means two. Bi also means two, like a bicycle, but in chemistry, bi, when referring to nomenclature, means hydrogen. And so if we wanted two, we'd use a D, di. And so if you see bi, these are rules. These aren't laws. And so you have bicyclic compounds, which have 2 rings, rather than dicyclic. And so this is just all little bits and pieces of memorization. The only way you can memorize all this is go over it and over it and over it. Otherwise it's going to be a huge. In fact, it turns out to be a huge jump. This is why so many people have such a hard time in organic chemistry. Organic was okay. The nomenclature wasn't that hard. Like ethanol. Ethanol is the most common alcohol. And so if you know this, that's pretty good. I'm about to give up on it. I don't want to deal with this anymore. Anybody else have this kind of problem? No? I'm going to reduce the window size here. all these remote programs on here. So ammonium nitrate, soluble salt. Ammonium itself is a weak acid, and so ammonium will partially ionize. When ammonium partially ionizes, and so this is a two-step one. And so we have ammonium nitrate. So first, it's a soluble salt. Soluble salts are strong electrolytes. That's going to form ammonium and nitrate. Ammonium itself is a weak acid. And so this is step one. In step two, we look at our ammonium. Ammonium being a weak acid partially ionizes, so this is uphill, but there could be a violent collisions. That means, you know, when we think about water, you know, are all the water molecules in your cup of water moving exactly the same speed? Can you imagine if they all moved in sync? They're not synchronized. They're just moving randomly. Even though they're moving randomly, do you think they all have the same energy? What do you think? You have an Avogadro's number in 18 milliliters. This is I don't know how many moles of water this is. That's a lot. But do you think they all have the same energy? They might be moving different directions, but do you think they all have the same energy? It turns out no. And so some of the water molecules are going to be moving a little faster. The ones that are moving a little faster might be able to make it up the hill. Up the hill to what? Up the hill to, well, this is a weak acid. You know, it's going to be harder. If ammonia got into a tug of war with water, ammonia should win. But sometimes water is a little stronger and water will win. But anyway, it forms a little bit of ammonia and hydrogen ions. So this is a weak acid. This is weak, it just partially ionizes, and this is why we saw some electrical conduction yesterday. Well, not actually, this is not. We didn't have ammonium, did we? We'd see a great electrical conduction here. And then we'd have an even bigger boost because we'll get a little bit, actually we won't. This is going to be the same, 1 to 1. It doesn't add any ions. So, that's ammonium nitrate. H2SO4 is also a two-step deal. H2SO4 is two-step because in the first step, what do we form? This is from yesterday. I know it's from yesterday. But you know, they say, because I was, what was it? I was taking biochemistry. And the biochemistry professor gave us a 25-page how to study pamphlet. It didn't work at all. And so for me, it didn't work at all. And so then I started looking for other sources. And so I ended up reading a lot of different things and trying different things at the time. But one of the things is how fast you lose memory. So like the next day, how much of yesterday do you remember? You know, and they have some kind of percentage. It depends on how much attention you're paying. You know, how much attention were you paying to, you know, I don't know how you got here, you know, during the drive. Do you remember all the details of that? Yeah, maybe it's still pretty fresh. But, you know, yesterday, day before, last week, you know, these types of things. But, you know, they say you lose like at least, what is it, 30%? Or maybe was it 60%? A lot. I just remember, you lose a lot. And as the time starts ticking, you start losing. So usually, if we go through some stuff, and I think I need to know it for the test, then I try to review it right after class. And so, one of the things is, after class, I just go back and review everything. And then it's fresher. And then the next day I'd review it again. And so I always try to reserve a block of time after class to review, because then I remember the most. You know, this is just minutes after class, and it's easier to remember.
Also, I guess depends on how intriguing it is. Like for instance, yesterday's little rocket thing. That's not gonna leave our memories.
Okay, well, that's good. That's good. So you know, the sugar rockets, yeah, there are a ton of videos. There are some really impressive sugar rockets. But I also do ethanol rockets. Maybe I should build an ethanol rocket. We could do that.
That'd be awesome.
But the ethanol rocket will disappoint you compared to the ethanol rockets on. We'll do
So
an
I
ethanol
was-
rocket.
What was the combination again? It was potassium chlorate or
Is it potassium perchlorate and sugar?
Not perchlorate. Perchlorate would have been more spectacular.
okay, so it was potassium chlorate, right?
Yeah, potassium chlorate.
When I was looking at, I guess, what color it should be, it said it was purple. I don't remember it being purple.
Potassium permanganate is purple.
Okay.
Potassium permanganate is dangerous stuff too. Potassium permanganate. For example, you don't want to mix potassium permanganate with sodium chloride. You know, sodium chloride, I told you, was very stable. But if you take potassium permanganate and mix it with sodium chloride, you know what you make? Well, potassium ions, do they do much? Nah, they don't do much. Potassium ions are really stable. Permanganate ions, do they do much? Yeah, the permanganate's dangerous. Why? Dangerous.
So oxidation state of the manganate.
Yeah, the oxidation state on what is pretty high. Manganese. Manganese oxidation state is what? Plus 7. That's really high. And so permanganate is a powerful oxidizer. Is permanganate going to oxidize potassium ions? No. I mean, potassium ions are already oxidized. Well, will permanganate oxidize sodium ions? No. No. Sodium ions and potassium ions, they aren't going to lose any more electrons. What could lose electrons? Yeah, chloride can lose electrons. And this is what happens. Chloride is pretty stable. It's not very reactive. But if you have something very powerful like this, then this is going to attack that and take the electrons. When potassium permanganate takes electrons from chloride, do you know what we form? So chloride loses electrons to form what? Chlorine gas. So something like this purple, it looks like grape juice, and it doesn't look so dangerous, but it's pretty dangerous stuff. And you can form chlorine gas easily. In fact, this is how we generate chlorine inside the laboratory. So if you just want a little bit of chlorine gas, you know, it's easy to make. Just get some potassium permanganate and mix it with some sodium chloride or hydrochloric acid or anything that contains chloride, and we can make a little bit of chlorine. If you want a lot of chlorine, then you just buy it. So the potassium chlorate, do you recall what color potassium chlorate was? White. Yeah, it's a white solid. It's a white solid or colorless. It could be clear. It depends if you look at a single crystal. You know, it'll be clear, colorless. It's a white powder that we use. And then we mixed it with sugar. And that was it. And then I used a little bit of this to set it off, to heat it up. It just needs a little bit of heat. So, what is this? Sulfuric acid, so a little bit of sulfuric acid. Sulfuric acid, do you recall it was 2 steps? What were the 2 steps? This first step,
Hydrogen ion and bisulfate.
yeah, hydrogen ion and bisulfate. In the second step, what happened? The bisulfate partially dissociated. And so these types of things are a bit more complicated. So H2SO4 is a strong acid. One of the 7 common strong acids. So strong acid is strong electrolyte. But it turns out that both of the hydrogens don't break off. Just the first one breaks off easily. The second one is harder to break off. And so in the second step, HSO4 minus, this is a weak acid. This is an acid anion, bisulfate. And this is going to struggle a lot more. And so what we end up with is a little bit of H plus and sulfate here. This, even though it's a weak acid, it's fairly strong weak acid. It turns out it's about 90% this and about 10% ions here. And so it's on the stronger end. A lot of these weak ones are really weak. That is, it's like 99%. So about 10% of these can make it up the hill. You know, 90% are going to be stuck at the bottom. They can't make it to the top of the hill. So that's what we have. Okay, so that's kind of what you do for these. This is good nomenclature practice here as well. Let's just zip through these, name them. This,
Calcium, no.
calcium metal, good.
Hydrogen.
Okay, now we have 2 choices here, and they're emphasizing that we have 2 choices. One, it's HCl gas. HCl gas is pure. And the other is HCl aqueous. And so the convention is, if it's HCl gas, we're not going to name it as an acid. We're going to name it as an ionic compound. So if you name that as an ionic compound, what do you name it? Hydrogen chloride. So we call this hydrogen chloride gas. And then this one would be hydrochloric acid. This one? Ammonia. Ammonia is a gas. And so we call it ammonia gas, or we call this one aqueous ammonia, because this gas dissolves in water pretty easily. These 3 are molecular. This is just an element. It's going to form what we call a metallic lattice. Metallic lattice is a lattice of metal atoms. So this is ionic, right? Metal and non-metal. This is called, yeah, but it's liquid, so we call this molten magnesium chloride. We'd have to melt this to do that. This one would be,
Potassium chloride.
yeah, potassium chloride.
Dihydrogen sulfide.
Okay, this one,
Uric acid.
for acids, these are all these little nuanced rules that people just memorize, and it's a pain to memorize all these, and so the more repetition, the better. When we have an acid, we don't use like for example, did you call this monohydrogen monochloride? No, we just call this hydrogen chloride. I know it's a bit of a pain. This is a binary molecular compound, but for acids, it's different. You know, this is a normal binary molecular compound. That's not an acid. That's fine. But this is an acid, so we don't name acids using the rules for binary and molecular. We name these as ionic compounds. And name this as an ionic compound, this would be called hydrogen sulfide. And so this is hydrogen sulfide gas. Just like this one, we don't call this magnesium dichloride. When we name ionic compounds, we don't have to tell you how many there are. And so this one, we don't have to tell you how many there are because sulfide's -2, so we need 2 hydrogens for that. So this is hydrogen sulfide gas. This is called hydrosulfuric acid. Good. A lot of people can't get that one. That's pretty hard. A lot of people on tests will call this sulfuric acid. This one is,
Tetraphosphorus decaoxide.
yeah, that's right, tetraphosphorus decaoxide. So here's the other thing. They don't like the double vowels, so decaoxide. Rather, they like to get rid of the A and call it decoxide. And so this is called tetraphosphorus decoxide.
We were talking about that yesterday when we were studying. If it's on a test
Mhm.
and we don't get rid of the double vowel, will you mark that incorrect?
No. I don't care. If you call it decaoxide, it's incorrect, but it's a minor error. What you're gonna find is you're gonna find lots of names for a lot of these things. So here, tetraphosphorus decoxide, or tetraphosphorus decoxide. Tetraphosphorus decoxide is what we're supposed to use here. And people name it different things, including the ionic. They name this as an ionic. Phosphorus likes to form +3 and +5. And so they're calling this phosphorus 5 oxide. Well, if you know the charge on phosphorus, you can figure out the ratio between phosphorus and oxides. So they're naming it as an ionic compound here. This one is, they're naming it using the empirical formula here, which is diphosphorus tetroxide rather than tetraphosphorus decoxide.
Nitrogen.
But this isn't even complete because they didn't use a double vowel on this one here, like pentaoxide.
That's the one we were working on yesterday, nitrogen tetroxide or dinitrogen.
So all these little
Yesterday we learned
things,
tetra.
become a bit of a pain.
So that's the dinitrogen, could be nitrogen.
What's this one, Jay, called?
Acetic acid.
Mm-hmm. Good.
Going
Yeah.
back to the spelling or the multiple names, if we have N2O4, can we call it nitrogen tetraoxide or dinitrogen tetraoxide?
It has to be dinitrogen.
Okay.
It's got to be dinitrogen tetroxide. N2O4. Dinitrogen tetroxide is a common chemical.
Is that rule where you, like with hydrochloric acid, where you name the gas an ionic, as an ionic compound, apply to all of those? Or
No, it doesn't, unfortunately. So this is pure acetic acid. In pure acetic acid, if we followed that rule, it should be hydrogen acetate, named as an ionic compound. But people never call it hydrogen acetate. People call this glacial. Remember this? Glacial. What? Acetic acid. This one's called glacial acetic acid. Pure.
so is the only way to remember this, like just to go through each one of them?
Right.
It's just hard when there's not a rule.
Right. It's just memorization, unfortunately. Some people won't have it memorized, but you know, this is like learning the new language. You know, and so you need to talk with that language. If you start naming things weird, then people aren't going to know what you're talking about. And when you start talking weird, like you come up with some weird nomenclature, then you're automatically not part of the group, you know. Part of the group, they're gonna kind of say, this person is weird, you know, what are they calling this, you know, hydrogen acetate. Nobody ever calls it hydrogen acetate, but, you know, you'd be corrected and eventually you'll figure it out. And so this is why that everybody gets into these little niches, and these little niches, they have their own jargon, and it takes time to pick up that jargon. So when you go to conferences, you hear people talking and you go, I don't understand any of that because, you know, you're not part of that and you don't understand their vocabulary. But for certain things like this, like glacial acetic acid, I'm not going to test you on that, but that was something we had yesterday. You know, I don't know if you remember or you don't remember. But when, you know, when like, when you have a lot of, pre-med students in the class, it makes a difference, because pre-med students, you know, they might have been dreaming to go to med school since kindergarten or something like that, and they're very serious about their dream. You know, they've been pursuing this dream for how many years? They wanna go to med school, and they're gonna do whatever it takes to get into med school. And so if it means memorizing every little thing that was discussed in class, they'll do it. And so you'll hear this stuff, you'll go, wow, you know, why do they know that? How do they know that? You know, because they're just on top of it. They don't want just an A, they want the top grade in the class, you know. This is a dream. Unfortunately, you know, not everybody can get the top grade in class. And so, and then people end up changing their plans, and some people pursue it and continue. You don't have to get the top grade in the class, you know, to do well. I have plenty of friends who got into med school who didn't have the top grade in class, just did all right. So here, what's this?
Copper sulfate, aqueous.
Yeah, copper 1 or copper 2?
Copper 2.
Copper 2 sulfate. So all sulfates are soluble, except for which one?
There's a lot of exceptions.
Yeah, this is the longest list. Silver, lead.
Mercury 1, Mercury 2, calcium, strontium, barium.
Yeah, usually I just say, okay, sulfates are soluble except for silver, lead, mercury, calcium, strontium, barium, you know, something like that. That's how I memorized it. We already named these, right? What was this one here?
Iron 3 chloride.
Iron 3 chloride. Okay. This one?
Potassium cyanide.
Potassium cyanide. Potassium cyanide is toxic stuff. You know, cyanide, they have, people talk about cyanide. And so, this is gas, hydrogen cyanide. Potassium cyanide is solid, it's a white powder, typically. Is it soluble in water? First you look at the cation. Is it soluble in water? What's a solubility rule number 1?
Salts are soluble.
Which salts are soluble?
Group 1.
Group 1. Is potassium group 1? Yeah, so group 1 salts are all soluble. So this should be quick. Potassium, group 1. Cesium. Cesium, group 1? Yeah. So the potassium salt and the cesium salt should be soluble. So potassium cyanide, you don't want to mix this with acid, because if you mix potassium cyanide with acid, it makes hydrogen cyanide gas. It's a double replacement reaction. Double replacement reactions we'll look at today. What's this called?
Lead 2.
Lead 2 chloride. Is it soluble? No, it's not soluble. It's insoluble. Solid. So we'd write a little solid here. This one could either be solid or aqueous. And so, what are the major species that form when the substances are added to water? So this is soluble salt. It's going to form.
Potassium ion and cyanide ion.
Yeah. This is insoluble. So the major species is just PbCl2 solid. It's not going to really dissolve. Minor species, a tiny bit will dissolve. So the major species will just be PbCl2 solid. HBr is called, now this is ambiguous because there's no AQ and there's no G here. Hydrogen bromide is gas, but when we dissolve it in water, we call it hydrobromic acid. And so if it's not specified here, we're gonna name it as the acid. This is gonna be called hydrobromic acid. Is it strong? Yes,
Oh.
it's strong.
Yeah.
It's one of the 7 strong ones, so what's going to happen? Is strong acids or strong electrolytes is going to break up into what and what?
Hydrogen ion.
Yeah, hydrogen ion and bromide ion. So those would be the major species. This is a soluble salt. It's also a strong base, but primarily we look at it as a soluble salt. Soluble salts will break up into cesium plus and OH minus. Don't forget the charge. A lot of people forget the charge. If you forget the charge, then that's a serious error. It's a serious error because charge is everything in chemistry. Chemists are mostly interested in electrical interactions. You aren't going to have any electrical interaction with no charge. We need to know the charges. Ammonia is a bit tricky. Ammonia is a weak base. There are 2 things that can happen in water when we have an acid or base in water. Acids, we could have, dissociation. Dissociation we also call ionization. We form ions. Dissociation, and there's another thing that can happen. The other thing is called hydrolysis. So when we look at HCl, HCl is a strong acid, and so if we're looking at HCl aqueous, then it's going to dissociate into H plus and Cl minus. But what can also happen is a water molecule can come along and pluck that hydrogen off. Water can act as what we call a base. Bases can take the hydrogen off. So if we have HCl and water, the water comes along and helps pull the hydrogen off the chloride and forms H3O plus chloride. This is hydrolysis, and they're equivalent, essentially. We think of them as one of the same because is a proton stable alone in water? Protons aren't stable alone in water, so they're going to pick up water anyway, so they're equivalent. And so when we do this, this is the shorthand way. If we don't want to do too much writing, this is a lot easier. But in the back of our mind, we know that protons are not stable. For bases, there's no dissociation. Only hydrolysis. And so when we think about acids, make H plus or hydronium in water. H plus hydronium. The opposite of H plus or hydronium is hydroxide. And hydroxide is the base. Acids can be ranked. So for example, the stronger the acid, the more H plus and the more hydronium we make. Let me insert this here. If we had a weak acid like acetic acid only partially dissociates, And so we could write it like this. Or only partially hydrolyzes. Hydrolyzes is hydro stands for water, and lysis. Hydro is water, lysis is breaking apart water. And so when we hydrolyze water here, we're breaking apart the water molecule to form hydronium and acetate. So for acetic acid, this is uphill. For hydrochloric acid, this is downhill. So for hydrochloric acid, this is super easy, and we form lots of H plus and lots of hydronium. For acetic acid, this is quite an uphill climb, and so we form just a little bit of H plus and acetate, or hydronium and acetate. So this is the difference between a weak acid and a strong acid. Strong acids supply lots of H plus or hydronium. Weak acids supply just a little bit of H plus or hydronium. And we can see this in electrical conductivity. Electrical conductivity of HCl was very strong. For acetic acid, it was much weaker. For bases, hydroxide is a strong base. And these strong bases, what they do is they don't dissociate completely, they hydrolyze completely. So if hydroxide and water react, then we're just going to form water and hydroxide. Although there's really no change there. There's no change. We're going to have lots of hydroxide. But if we have a weak base, the weak base is going to try to pull the hydrogen off water. And so we have ammonia here and water. But this is kind of uphill. Water doesn't want to lose that hydrogen. But if there's a strong enough collision and they get into a tug of war, then what's going to happen is some of it will be lost. And so we'll form a little bit of ammonium and a little bit of hydroxide. And so in bases, we look for hydroxide. A strong base has lots of hydroxide in water. A weak base has just a little bit of hydroxide in water. And so it's not really the ammonia. It can be the ammonia, you know, that we focus on. It's the hydroxide. How much hydroxide are you producing? Either you'll have it originally present, or you form some due to hydrolysis. Hydrolysis will form the hydroxide. When an acid reacts with a base, we form water, like this. Hydronium and hydroxide, or hydrogen ion and hydroxide, will form H2O. These are called Bronsted acids and bases. Or Arrhenius. So the minor species here,
I'm looking at the hydrochloric acid example. Why would hydrolysis even happen? Because aren't they both stable, like water and hydrochloric acid? And then, you know, why would the water even take the hydrogen?
This is still called hydrochloric acid. The water is going to take the hydrogen because having the free protons too reactive. This is H plus aqueous. And so it's just going to happen automatically. When you take hydrogen chloride, the water is going to attack it. And the water is I probably should talk about the driving force. This is downhill. It's downhill, so when we do an acid-base reaction, we compare the two acids. So this is the acid going forward. This is the acid going backwards. And we look at which way is downhill, which way is uphill. And then what we do is we go over here and look at which one's more stable. stronger it is, the more reactive and the less stable. And so the strongest here is HCl4. It's going to be the most reactive, least stable. And then we have HCl here. And HCl is pretty reactive. It's a pretty strong acid. But then what do we have here? Hydronium. Hydronium turns out to be more stable energetically. And so this is downhill. We're going from HCl, which is what we call a stronger acid, to hydronium, which is a weaker acid. It's more stable. This one is going uphill, as it's forming H+. And so H+ is less stable. And so this is going from stronger acid to weaker acid. Now, you know, the acids are different strengths. Is this uphill or downhill? So when I look at this, I'm comparing acetic acid. This is the acid in the forward direction. The acid in the reverse direction is hydronium. So I'm comparing acetic acid with hydronium. And so if we take a look over here, acetic acid is here. This is another way of writing acetic acid, CH3COOH. And hydronium's here. Is that uphill or downhill? That's uphill. This is uphill. It's not going to be as stable. And so it's reacting. The hydrolysis happening is because the proton's not stable. And we can have that reaction. Over here, the hydrolysis happening is because this is a reaction that's potential. When you have a violent collision between ammonia and water, bonds can be broken. You know, the bonds holding the atoms together can be broken. But this is quite uphill here, because when we compare ammonia, which is a weak base, to hydroxide, which is a strong base, and we have here. And so we'll need the acid-base chart over here. And so the strongest acid on the chart is perchloric acid. The weakest acid on the chart is this. CH4 is called methane. We don't even think of methane as an acid. It's so bad. But methane could potentially lose a hydrogen. It's so bad we don't even write the hydrogen in front. We write it in the back here. These hydrogens don't want to react. You know, same thing here. The hydrogen doesn't want to react. And so it's written behind the nitrogen. Whereas an acid, this hydrogen wants to react. It's written in the front. All these acids, the hydrogen is written in the front, including water. Water can be an acid. If water loses that hydrogen as a proton, we're left with hydroxide. Well, anyway, so hydroxide here, these are all strong bases too, but I'm not going to talk about these. I'm going to skip these strong bases. Last time I talked about the class, I covered all these. We cover these in Chem 1A anyway. Well, water is unusual because water can both be an acid, it's a pretty weak acid, and it could be a base. Yeah. It's a pretty weak base. And the interesting thing is it's equally strong as an acid and as a base. So it being equally strong as an acid and base, we call it neutral. You know, some things are a lot better acid than base, and some things only can act as acids. Like HCl can only act as an acid. It can't act as a base. But hydroxide can act both as an acid and a base. Ammonia can act both as an acid and a base. But ammonia is a much better base than it is an acid.
Should we memorize the strong bases?
No. The question is, should you memorize the strong bases? No. In Chem 1A, yes. You should know the strong bases. So ammonia being a base is tricky, because bases hydrolyze water. So to figure out the minor species, the major species, and base solutions, you have to do the hydrolysis. You can't dissociate ammonia. What's this called? Oxygen. Oxygen is strong acid? No. Strong base? No. Soluble salt? No. Weak acid? Weak base? Heavy metal salt? All right, process of elimination tells us it's a non-electrolyte. So major species will just be O2 gas. O2 is not very soluble in water. You know, ammonia loves water. O2 not so much. And so you can dissolve lots and lots of ammonia in water. You can't dissolve much O2 in water. And so we call O2 insoluble in water, but insoluble means it's not completely insoluble. A tiny bit of O2 will dissolve in water, enough to support marine life. G.
Phosphoric acid.
Phosphoric acid. Strong acid or weak acid? Weak acid. Weak acid is only partially ionized or hydrolyzed in water. For Chem 4, we just do dissociation for acids, and we do hydrolysis for bases. Situation is, what does it dissociate into? And so the question is, how many hydrogens? See, all three hydrogens are written in the front, which means all three are actually acidic. This one we call a triprotic acid because it has 3 protons that it could give out. Sulfuric acid is called a diprotic acid, and hydrochloric acid is called a monoprotic acid. And so with this triprotic acid, we have 3 hydrogens that can break off. However, all 3 don't break off at the same time. Just the first one breaks off. So if the first one breaks off, then we're left with H2PO4 minus. H2PO4 minus is called what? It's the name for H2PO4 minus. Yeah, this is called dihydrogen phosphate. Now, why didn't we name this as an ionic compound? If we call it hydrogen phosphate, then it could be mixed up with H3PO4. This is only step 1. How many steps are there? 3. So we'll just say etc. because I'm not going to write the 3 steps there. The next step is some of the dihydrogen, which is even the weaker acid, dissociates. And the final step is what we call monohydrogen phosphate. Monohydrogen phosphate dissociates to very small extent. So those are going to be the major species, though, for this. Unfortunately, they aren't asking us for the minor species. Otherwise, we'd have to do step 2 and 3 to get the minor species.
Isn't the major species just H2?
Oh, yeah, you know what? That's it. There are lots of minor species. The major species is H3PO4. You're right. Because this is uphill. And so most of it will stay down at the bottom of the hill.
In what state would we write that in? Alkylates, or would it be solids? and
No,
stuff?
it's aqueous. Because we're adding it to water, and acids are soluble in water. Acids, for group 1. You put hydrogen in group 1. This one's interesting. What's this one called?
It's just aluminum sulfate.
Yeah, just aluminum sulfate. And is aluminum sulfate soluble or insoluble?
Insoluble.
Sulfates are all soluble except for silver, lead, mercury, calcium, strontium, barium. Was aluminum in that list? No, so it's soluble. If this is a soluble salt, what do we form? we're gonna form how many aluminum ions? So it's a soluble salt. So Al2SO4 3 aqueous is going to form 2 aluminum ions and how many sulfates? 3 sulfates, if we wanted to balance this. And so the major species are this. Next one is called zinc hydroxide. Soluble or insoluble? So hydroxides are all insoluble except for group 1, ammonium, calcium, strontium, barium. So is that one of the exceptions? No, so it's insoluble. Insoluble salts are non-crystallite. So this is the major species here is just going to be zinc hydroxide solid.
What was the states for those?
Aqueous. These are all aqueous.
So for the drink, the zinc hydroxide, that's gonna be Zn2 plus and OH minus?
No. It's an insoluble salt. So the major species is just
It's just that.
solid, yeah. It's insoluble, but a tiny bit might dissolve in water, but the tiny bit is what we call the minor species. The major species is what we have here, zinc hydroxide salt. Sulfuric acid, what are the major species here? Strong acid, strong electrolyte. Hydrogen ion and bisulfate. Step 2 is minor, but step 1 is major. And so hydrogen ion and bisulfate ion. What's this called? Ethanol. Strong acid? Strong base? Soluble salt? Weak acid? Weak base? Heavy metal salt? And then we're out of options, so this is non-electrolyte. The major species are just going to be ethanol molecules dissolved in water. The ethanol molecules don't dissociate in water.
What would be the charge of that though?
Zero. Zero
Okay, so it's
charge.
just itself?
Yeah, it's not going to conduct electricity.
Would that be a liquid or
Aqueous.
aqueous?
Yeah. Water, strong acid, strong base, soluble salt, weak acid. Yeah, a little kind of a weak, super weak acid. If it's a weak acid, what's a major species? It's a weak acid and a weak base. Major species is just going to be H2O liquid. Barely dissociates.
Can you, real quick, go back to the H plus SO4 2 minus? The H plus would be the gas,
No. It's aqueous.
aqueous, and the
H2 is a gas. And so H2SO4 is a strong acid, so it's going to dissociate into H plus and HSO4 minus. These are the major species here. There is a step 2, but step 2 would be minor. So all of this is downhill. We're gonna lose all of these. Everybody can make it down the hill. Even, making it up the hill is more problematic for some of the population, but making it down the hill, everybody should be able to make it down the hill. And so we should have complete,
So that,
It depends on how steep the hill is, because some people can make it down the hill and then reverse and go back up, The really aggressive ones might want, they might not be happy just being downhill, they'll want to go back up the hill. And so sometimes you'll have that happen, but if it's a really steep downhill, then even the strong ones, they probably aren't gonna wanna go all the way back up the hill.
So both of them will be aqueous?
Yep. Aqueous and aqueous. Now, for chemical reactions, you have two options for getting practice. Beyond the book. These are the reactions in the supplement here. And these are the reactions on page 1. Magnesium is burned in air, magnesium oxide is added to water, sulfur trioxide gas is bubbled into water. These are certain patterns, these are some additional patterns. You're supposed to, in this class, you're supposed to learn a whole bunch of patterns, not just the ones we talked about. What are the patterns that we talked about? It was the element plus element combination. Right? Single replacement, double replacement. The reactions in here, they have a few additional patterns, but I think I'll probably skip those for now. We're going to be looking at net ionic equations here next. And we're going to be looking at net ionic equations using the basic patterns that we studied here, the simple ones. If you want to know all the patterns that you need to know for the chemical reactions that you're supposed to know, they aren't summarized here. We'll just focus on the simpler patterns first, and then maybe we'll look at the other patterns later. Let's we'll take a break now, and then we'll start this next. This was from the supplement, net ionic equations. Yeah. Right. The supplement has a lot more reactions in the book. So it's good.
It's like if you want to study like outside of the book.
So here we have potassium is added to water. And I'm writing water as an ionic compound, sort of, like hydrogen hydroxide. And the reason I'm doing that is to get it in the form. What form am I trying to get this in? The A plus BX form. If I get it in the A plus BX form, then that's what we call single replacement. And this should form what? Yeah. This should form potassium hydroxide and hydrogen gas. Okay, then we use what's called in order to determine if there's a driving force, we use the chart or the activity series. And so if this is single replacement, then we'll probably want to use the, what we call the activity series. The activity series. However, the activity series is not all the way until chapter 19, so you might want to Not all the way until chapter 19, it's in the strength here. So we go out to chapter 19 and look at the strength. Then we go to page 567. And so when we have single replacement, we compare the two elements, A and B. So what are the two elements we're comparing? Potassium versus hydrogen. So let's take a look. Here's potassium, here's hydrogen. Which way's downhill? Potassium to hydrogen's downhill or hydrogen to potassium's downhill? Potassium to hydrogen's downhill. So this is going to be downhill. In other words, we're going from the, what we say is the more active, that is, it's higher up on the activity series, to the less active. This is why it's written backwards, because this way it's easier to see which way we're going downhill. On this chart, lithium's all the way at the bottom, so we'd have to be upside down to see this. But here we put lithium at the top. Okay, this is not balanced, so how can we balance this?
Two potassium hydroxides.
Yeah, two potassiums,
Two potassium hydroxides.
two potassium hydroxide,
Two waters.
two waters. Okay. What's the state for water? Liquid. Potassium salt are group 1 salts. Group 1 salts are all soluble salts are all strong electrolytes, or soluble, I should say, and they're strong electrolytes. This is what we call the full formula equation. So this is A, the full formula equation. Now for the total ionic equation, this is what we do for part B. For part B, you're going to dissociate the strong. Dissociate strong electrolytes only. Leave everything else. If it's weak or non, just leave it alone. So is potassium metal a strong acid? Is it a strong base? Is it a soluble salt? Well, if it's a salt, it needs a cation and an anion. Does it have a cation? So it's not a salt. Is it a weak acid? Weak base? Well, if it's not strong, I don't even have to go through that. I only have to see, is it a strong acid, strong base, or a soluble salt? Anything else, we're not going to touch. So this is not strong acid, strong base, soluble salt. Leave it alone. Is water a strong acid, strong base, or soluble salt? No, leave it alone. Except in this case, I'm going to write it as H2O liquid rather than HOH. Is KOH a strong acid? No. Strong base? Well, first we treat it as a soluble salt. Group 1 salts are all soluble. So if it's a soluble salt, then we're going to dissociate it. What's it going to dissociate into? Yeah, K plus and OH minus, but we're going to keep it balanced. So we're going to form 2 K pluses plus 2 OH minuses. Hydrogen gas, strong acid? No. Strong base? No. Soluble salt? No. So just don't do anything with it. We're just going to call it hydrogen gas. So this is called the total ionic equation. And so this is showing all the species that are present. So we have potassium metal water molecules, but once they react, then we're going to get potassium ions and hydroxide ions, AQ, and hydrogen gas bubbling out. And so the product of this reaction, so before the reaction starts, we get chunks of potassium metal that we're dropping in water. After the reaction has taken place, we can see what we formed here. We're going to form potassium ions, hydroxide ions, and hydrogen gas. The hydrogen gas is not soluble in water and will bubble out. And so we label this beaker KOH, AQ, from 2 KOHs. But the total ionic equation here gives us more details, as to what's happening here. It's not just KOH, it's actually potassium ions and hydroxide ions dissolved in water. And then we have the hydrogen gas bubbling out. Sometimes there are species that don't do anything, and those are called spectators. And so in part C, we do the net ionic equation. The net ionic equation is getting rid of any spectators. But there are no spectators here because the potassium participates in the reaction. Water participates, and that leads to potassium ions, hydroxides, and hydrogen. And so no spectators here. And so this is an example of a single replacement reaction. We had driving force here. And so we're okay. If there's driving force there. Two, hydrogen chloride is bubbled through aqueous lead-2 acetate.
So is C gonna be the exact same as the total ionic equation?
Oh, yeah. No spectators, so same as B. The net ion equation. Net ion equation and total ionic equation are the same. Number 2, I don't like so much. Because the reason I don't like it is because it depends on the instructor what the answer will be, what their preference is. Hydrogen chloride. Is hydrogen chloride soluble in water? Yeah. Hydrogen chloride soluble in water. If you bubble it through water, you know what it's going to dissolve in the water. When it dissolves in the water, we don't call it hydrogen chloride gas, we call it hydrogen chloride aqueous, and hydrogen chloride aqueous is called hydrochloric acid. And so this is the way I'm going to do it. I'm going to do it like this. If I take hydrogen chloride gas and then bubble it in water, then automatically I'm going to get hydrochloric acid type. And so in this one, I know some instructors will want you to leave it as hydrogen chloride gas. This is fine. Maybe we should. If we left it as hydrogen chloride gas, then we'll just say HCl gas. Or you could write HCl aqueous because that's reacting, but it looks like we're going to have to buy HCl gas if we want to do this as written. Because the HCl aqueous is just going to be a bottle of liquid hydrochloric acid. Okay, so we'll buy a bottle of hydrogen chloride gas, and then we're going to bubble it through an aqueous solution of lead-2 iodide. Or not iodide, acetate, lead-2 acetate. So we have to figure out what the formula for lead-2 acetate is. Now, lead-2 is just Pb2+. What's acetate?
C2H3O2.
Yeah, good. And how many acetates will we need for this? 2. So lead-2 acetate, PbC2H3O2. And this is aqueous, so we'll just write aqueous here. And do you recognize this pattern? This pattern is the AB plus CD pattern. And what does it yield?
Lead to chlorine.
Yeah. what I'd like to do is I'd just like to switch the anions. And so I'll have the hydrogen cation with the acetate anion. Hydrogen acetate, we don't call it hydrogen acetate. What do we call hydrogen acetate? Acetic acid. So we're going to form acetic acid. And lead with chloride. Lead with chloride is going to be called lead chloride, but more specifically lead 2 chloride. Acids are soluble, so we're going to call this one AQ, aqueous. Chlorides, bromides, and iodides are insoluble, except for which ones?
Except for silver, lead,
Except for silver, lead, and mercury. So this is a solid. And so what we end up getting is a precipitate here, PBT. And so this is a cloudy white precipitate that forms. This is what we call driving force for the reaction. When we have a double replacement reaction or metathesis reaction, let's look at the driving forces for double replacement reactions over here. They're different than for single replacement. Single replacement, what was the driving force for single replacement? Was the activity series? What's the driving force for double replacement? It's not the activity series. There's no element. You know, we can't compare element A versus element B. There's no element. A is a cation, B is an anion. So what we do for double replacement, it just needs one. We don't have to have all three present. And so there's three driving forces that we look for. One is precipitation. Precipitation is formation of an insoluble solid. So we formed an insoluble solid, PbCl2, so that's precipitate, and this is what we call driving force. 2, gas formation. Double replacement only. In single replacement, the gas formation is not a driving force. In fact, none of these work for single replacement. Precipitation as well. Double replacement only. Did we form a gas? No, we formed aqueous and solid. How do we recognize what are gases that we might form? The gases we might form, the big one is this. Do you recognize this acid? This is carbonic acid. Carbonic acid, aqueous, is unstable. And it automatically decomposes into water and what? Carbon dioxide. This is the big one. And so if we form carbonic acid, that's going to decompose into water and CO2, and CO2 is a gas, plus others. Three, going from a stronger acid, it doesn't have to be a strong acid, it could be a weak acid. It just has to be stronger on the left than on the right. So going from stronger to weaker acid, so we'll go downhill. This one happens to be a strong acid, HCl, hydrochloric acid. The weak acid is acetic acid. So we're going from a stronger acid to weaker acid. That's driving force as well. So stronger acid I call SA for stronger acid. Weaker acid I call WA for weaker acid. So we're going from SA, HCl, to WA, acetic acid. This is so all we need is one. In this case, we have two driving forces that are present. So this is a very favorable reaction. All right, this is equation A. Is it balanced? No. How can I balance this one?
2 HCl.
2 HCl,
and 2
2 acetic acid. Okay. Then it's balanced. All right, now we go to B. In B, we're going to dissociate or ionize the strong electrolytes only. HCl, is it a strong electrolyte?
Yes.
Yes. But it's in the gas. When it's in the gas, it doesn't really dissociate. And so what we're going to do is I'm going to do something with this. I'm going to put an intermediate step here. And so the intermediate step is HCl is soluble in water. HCl likes water. Like dissolves like. So if there's water present, we're going to form HCl aqueous. HCl aqueous is a strong acid, hydrochloric acid, and hydrochloric acid dissociates into what? Yeah, H plus and Cl minus, and to keep it balanced, we need 2 H pluses for every 2 HCl's and 2 Cl minuses for every. Now, writing AQ is 4 characters, takes time, right? And so what people do is they stop writing AQ, but they always write solid, liquid, gas. And so if there's nothing written here, it's aqueous. If there's something written, it's got to be solid, liquid, or gas. And so in this case, it's aqueous, but yeah, maybe I'd write it, maybe I wouldn't. This, I'm writing it here just to emphasize because we're going from gas to aqueous to aqueous. All right, so we expect the hydrochloric acid to dissociate. How about the lead 2 acetate? Do we expect that to dissociate? So first we look at the cation. Group 1 and ammonium are all soluble. Then we look at the anion, starting with nitrates, chlorates, and one more. Nitrates, chlorates, and acetates. Nitrates, chlorates, and acetates are all soluble. And so this is a soluble salt. If it's a soluble salt, then we dissociate it. Soluble salt's a strong electrolyte. This is going to dissociate into Pb2 plus, good. And how many acetates? I need 2 acetates. So it dissociates into Pb2 plus 2 acetates.
Is the lead, with 2 ions, is that aqueous or?
Yeah. This is aqueous and aqueous. Is acetic acid a strong acid? No, acetic acid is weak acid, so we just leave it alone. We don't touch it. Is lead 2 chloride a soluble salt? No, it's an insoluble salt. So insoluble salts, we leave it alone. We don't touch it. Are there any spectators here? Spectators don't participate. There are no spectators. So this is the same as this. And so what we do here for this is we try to visualize what's happening here. This one's harder to visualize. Maybe I'm going to skip the visualization of this one. Because this HCl gas kind of screws things in. But basically, what we're doing is we're combining ions. Like here, chloride loves lead, and so the chloride and lead will combine. And hydrogen ions like acetate, much more than they like chloride. And so we're just rearranging the ions to more favorable combinations of the ions. That's all we're doing, double replacement reaction.
So the net ionic will be the same?
Yeah, no, it's the same. We could leave this as HCl gas all the way down here as well. Let's skip number 3 for right now. Number 2 and number 3 are kind of ambiguous because we know the HCl is going to dissolve. We know when it dissolves, it breaks up into ions. But what we purchase is HCl gas. And so it depends on the instructor. You'll either always leave this as HCl gas or you can convert it. Here. Let's look at number 4. So number 2 and number 3 I would have put at the end. Because number 2 and number 3 are more complicated. Right now we'll just try to do the more straightforward ones, like number 4. Silver. What's his formula for silver?
Ag.
State?
Solid.
Should I put, is it Ag plus or 0? 0. So this is silver metal. Does silver metal dissolve in water? Have you tried to dissolve silver metal in water? What do you think? No. No, so we'll just keep it as solid. And copper 2 bromide. What's the formula for copper 2 bromide?
CuBr2.
Yeah, CuBr2. That's good. And this is solution. So what I'm going to do is I'm going to do this thing where I'm not going to write aqueous all the time. So if there's nothing written here, we'll take that as aqueous. This we don't want to call aqueous, so we'll have to write solid here. Make sure we differentiate it. What pattern is this?
Single replacement.
Single replacement. So it's A plus BX yields AX, silver bromide, and B. B is Cu. Cu plus, Cu2 plus, or Cu0? Solid, liquid, or gas? Okay, now silver bromide, is that chlorides, bromides, and iodides are all soluble except for silver. So silver is an exception. That means it's insoluble, and therefore we're forming an insoluble solid, which is called precipitation. But precipitation is only valid for what type of reaction? Double replacement, not single replacement. For single replacement, we cannot use precipitation and we cannot use gas formation. And we cannot use stronger acid to weaker acid. We have to use what? The activity series. So let's go back to the activity series. Do we really need it? You probably already know. Which one is less resistant, or which one is, I shouldn't say less, which one's more resistant to corrosion? Which one retains its shiny luster for longer? Silver or copper?
Copper.
Or how about this? What do you think is better? Silver jewelry or copper jewelry?
Oh, silver.
Yeah, probably silver. You know, if you made, let's say, copper teapot versus a silver teapot, I probably would rather have a silver teapot. You know, even though copper's pretty good. And so we already know silver is more stable. That means if silver is more stable, does that mean it's more active or less active? Yeah, so this is less active. And copper is more active. And so copper is more susceptible to corrosion than silver is. And so this is a case where we didn't really have to use the activity series. We can just try to figure it out. And so, in other words, this is a driving force. So this should be downhill. We're going from more active to less active. And so this should be downhill. Is it balanced? No, it's not quite balanced, is it? How should I balance it? 2 silvers, 2 silver bromides. And then, is it balanced?
Yeah.
Yeah. All right, so this is equation A. Equation B, we dissociate the strong acids, strong bases, and soluble salts. So a silver is a strong acid? No. Strong base? No. Soluble salt? No, it's an element, and so just leave it alone. Copper 2 bromide. Strong acid? No. Strong base? No. Soluble salt? Yes. It's soluble salt. So this is going to dissociate into, but we got to make sure we balance it. So how many bromides do we need for every copper? 2. So 1 copper 2 and 2 bromides. Silver bromide, strong acid? No. Strong base? No. Soluble salt? No. So don't do anything, just leave it alone. Copper metal? Just leave it alone, it's just an element. Boy, are we ever going to get to equation C? In this case, everything participates. Because copper 2 is converted into copper metal. Bromide is going to kind of precipitate with silver, but we don't worry about precipitation. And so the equation C is the same as equation B. Let's go to 5A. Zinc is added to sulfuric acid. So what is zinc? Solid, liquid, or gas? Charge? 0. Sulfuric acid?
H2SO4.
H2SO4. Solid, liquid, gas, aqueous? Aqueous. Acids are going to be aqueous. And when we look at this pattern, the pattern is an A plus BX. Now, what is X? We have 2 choices. X could be the acid anion bisulfate, or X could be the anion sulfate. Now, when we dissociate this, we only dissociate to bisulfate, but when we do a reaction, we're going to take it all the way to sulfate. And so this will form zinc sulfate, that would be AX. Zinc sulfate and, yeah. So what's the formula for zinc sulfate? Yeah, just the NSO4. And hydrogen? H2. Yes. How about zinc sulfate? Is that soluble or insoluble compound? So all sulfates are soluble except for silver, lead, mercury, calcium, strontium, barium. Actually, silver, lead, mercury, calcium, strontium, barium. So this is not an exception, so this is aqueous, so we'll just leave it alone. So is there a driving force for this? So we'll have to consult the activity series, zinc versus hydrogen, and then take a look at the activity series here. Zinc versus hydrogen. What happened to my activity series? Here it is. So zinc to hydrogen downhill? This is downhill. So this is, zinc is more active, you know, higher up in the activity series. Hydrogen is less active, lower down in the activity series, so this is downhill. In other words, this is what we call driving force. This. And so we expect this reaction to happen. That's fine. You get a reaction like this. Sulfuric acid turns out to be an oxidizing acid. It's an oxidizing acid where sulfate is a better oxidizer than H+. You can see it here. Here is sulfate. Here is H+. So sulfate's a little better. And so we can actually form potentially some other stuff in this reaction of oxidizing acids. But in this case, since H+ is plenty strong enough, the H+ will probably react pretty fast. So this could lead to a more mixed up reaction. But we'll leave it since it works. If there was no reaction here, then I'd start thinking about, hey, wait a minute, sulfate's a pretty good oxidizer too. So I'd think about that. You know, the oxidation state of sulfur and sulfate's +6. But this worked, so we're just going to go with this. Okay, zinc, leave alone. Sulfuric acid is a strong acid. So strong acids or strong electrolytes. Strong electrolytes dissociate into, well, this one's going to dissociate into what? 2H plus or 1H plus and 1 bisulfate. Or 2 H pluses and 1 sulfate. 1 H plus and 1 bisulfate. The reason it's doing this is because of water. Water is not strong enough to pull the second hydrogen off. That's who's pulling it off. Water, because both of these are aqueous. However, if I put zinc in there, then the zinc and the H plus can react. So zinc and H plus and HSO4 minus, that is the hydrogen and bisulfate can react. So zinc sulfate, is that a soluble salt? Yes. Figured that out. And so this is going to be Zn2 plus SO4 2 minus. And then hydrogen, it's just the gas. Yeah. This is close, but not quite there yet, because here the H plus got converted into H2. Is this balanced? Yeah, it's balanced. But the HSO4 minus and the SO4 minus, 2 minus are two different things here. And so there are no spectators. Everything participated, or everything kind of changed. And so it's the same.
So you said the reason why it's hydrogen bisulfate is because water is not strong enough to what again?
pull off that hydrogen. This one. This is dissolved in water. And so it just doesn't like break off naturally. Something has to break it off. And the water is what's breaking it off. This is always confusing because this is sulfuric acid, sulfate and H+. But the reason it's written separately here, you know, why isn't it bisulfate and H+? The reason it's written separately here is because we can get this mixture not from sulfuric, we can get this mixture from sulfuric acid. If we do that, then, but we can also get this mixture by taking, like, say, sodium sulfate and hydrochloric acid. That would give us acid and sulfate, which would make this oxidizer here. So there are different ways of making it. And so it's always confusing because you see sulfate here, but why isn't it bisulfate? Well, it should be bisulfate. Are we ever going to get a net ionic equation? I think so. I think this next one can give us a net ionic equation. So let's try this next one out here. All right, 6A, sodium fluoride. What's the formula for sodium fluoride? NaF. It says solution, so if it says solution, then you know it's got to be aqueous. And if it's aqueous, I'm not going to write anything here. And then nitric acid. What's the formula for nitric acid? HNO3. Good. And those are always aqueous as well. And so what pattern is this?
Double replacement.
Double replacement. So we're going to make sodium and hydrogen fluoride, but we don't call it hydrogen fluoride. So we're going to make sodium nitrate and hydrogen fluoride. And these are going to be, well, all sodium salts and all nitrate salts are soluble, so that's aqueous. And acids are soluble, so that's aqueous. So we are not going to call this hydrogen fluoride. We're going to call this hydrofluoric acid. All right, so this would be A. Is there a driving force for this? What is the driving force for double replacement? Okay, precipitation. We don't have any insoluble solids. So no precipitation. No gas, although hydrogen fluoride normally is a gas, so yes and no. But hydrogen fluoride is very soluble in water, so it's aqueous. And what's the last one? Okay, so what we need to do is we need to compare nitric acid with hydrofluoric acid. And so we go over to the acid chart and see nitric versus hydrofluoric, sorry. Here's nitric acid here. And here's hydrofluoric acid here. So if we go from nitric to hydrofluoric, is that downhill or uphill? That's downhill, so this is good. So we're going from stronger acid, nitric acid, to weaker acid, hydrofluoric acid. And that's what we need for driving force. This will be a downhill reaction, so it's good. In terms of energy. Okay, the next thing we do is B, which is to dissociate the strong. So sodium fluoride is a soluble salt. Soluble salts are strong electrolytes, so what do we do? Na plus and F minus. Nitric acid is a strong acid, so we dissociate into and NO3 minus nitrate. So hydrogen ions and nitrogen ions. Sodium nitrate is a soluble salt, which is also a strong electrolyte, so we're going to dissociate that into And hydrofluoric acid, is hydrofluoric acid a strong acid? No. Hydrofluoric is a weak acid, and so we don't do anything to it, we just leave it alone. Okay, now when we look at this, did the sodiums react with anything? The sodium ions? Now, we have sodium ions here, but we have them over here, so the sodium ions, this didn't react. Sodium ions are what we call spectators. They don't really participate in the reaction. And so they start off there and they end up there. Did the fluoride ions react? Yeah, the fluoride ions reacted with the hydrogen ions to make hydrofluoric acid. And so these two are not spectators. How about nitrate? Nitrate spectator here. And so in the net ionic equation, we get rid of the spectators. And so what we see is we got fluoride ions reacting with hydrogen ions to make hydrofluoric acid. That's what we'll have. So to visualize this, initially we have two beakers, let's say. One beaker is labeled sodium fluoride, AQ. But sodium fluoride AQ actually consists of sodium ions and fluoride ions, AQ. And then we combine that with another beaker. In the other beaker, it's labeled HNO3AQ. But HNO3AQ actually consists of hydrogen ions and nitrate ions. And then we mix these together. We add the acid, so we'll add the acid there. Makes it, I need a bigger beaker. But once I mix it together, I get reaction. Do the sodiums react? No. Sodiums didn't react. Did the nitrates react? No, the nitrates didn't react. But what did react was the hydrogen ions and the fluoride ions. The hydrogen ions and the fluoride ions came together to form molecules of HF. And so what we'll form here is we're going to form sodium nitrate AQ plus HF AQ. So this is what's happening. And then when you look at the spectators, we can get rid of the spectators. And so once we get rid of the spectators, we have this. And so what this says is any acid can react with fluoride to form HF. It doesn't matter what the acid is as long as it has H plus present. So we could use acetic acid. We could use hydrochloric acid. We don't have to use this, which is an oxidizing acid, the nitric acid. Okay.
How do you know what the driving force is? Like,
There are two driving forces. One set of driving forces for double replacement and another driving force for single replacement. And you can't interchange them. So you can't use the driving force for double replacement to predict single replacement and vice versa. Why don't you try number 7? The ammonium hydroxide is unstable. Okay, I forgot to do this for the recording. But this is the complete equation here. So if we're gonna form what was the first product? The first one was what? Potassium phosphate. So potassium phosphate is the first one. So this is a potassium ion. and the phosphate ion is PO4 3 minus. So if we're forming, actually, that's what we started with, right?
Yeah.
And so that's going to be K3PO4. That's potassium phosphate. And what was the other one?
Chloride.
Okay, cobalt 2 chloride. And so how many chlorides will we need for that? 2. And so what we're going to form here is potassium chloride. And so what I do is I just, look, potassium ions are this. I don't care that I have 3 of them here. I just want a potassium ion is K plus, and then chloride is Cl minus. So they should combine in a 1-to-1 ratio. If I have multiple, then I'll just put a coefficient in front. But this is potassium chloride here.
So you're gonna have to put a 3?
Eventually I'll have to put a 3 or some other thing here, at least. But that's, I don't have enough chlorides here, so I gotta figure it out. There's a mismatch. This is 3, that's 2. If one's 3, the other's 2, then the common factor is 6. But we can deal with that later. And the other product is going to be cobalt 2 ion with phosphate, but these don't match up either. This is 2 plus, that's 3. And so we do this cross multiplication type deal here. And that's going to form CO3 PO4 2. But I don't care about the numbers because the numbers, I change the coefficients in front to balance it. So if I have 3 potassiums here, I'll need 3 potassiums here. But how many phosphates do I have? I have 1 phosphate here and I have 2 phosphates here, so it's not going to work. And so what I need to do is I need to go 2 phosphates. And so if I have 2 phosphates here and 2 phosphates there, that screws up the potassium because now the potassium is 6. So I'll need 6 of these. And this one only has 2, so I'll need 3 of these. And then do you see its balance? So I don't worry about the numbers until we come to the balancing step. All you do for the formulas is you just make sure you have the right ratios to make it electrically neutral.
So I understand the potassium phosphate is aqueous. Oh, okay, and the cobalt 2 is, chloride is aqueous, but the products would be aqueous as well?
Potassium salts are all soluble. Cobalt salts we don't know, so we look at the anion. Phosphates are all insoluble. Phosphates, carbonates, and chromates are all insoluble except for group 1 and ammonium. So this is not a group 1, nor is it ammonium, so this is going to be a precipitate. And so what we say is driving force is precipitation, PPT.
So the driving force is like what makes the equation, or what makes the reaction occur, right?
Right. If there's no driving force, then what we say is NR, no double replacement reaction, is what we'd say. We have to have a driving force present. Sometimes there's no driving force present, so nothing happens. Leave it. The supplement, it's been a while since I looked at those supplement problems. Those supplement problems, a lot of those reactions are the next step or the next level. We just want to get the basic ones down first. The basic ones would be like these here in the homework, your book. So probably we'll take a look at some more reactions, I think, next time as well. But did you guys get the total ionic equation for this? Yeah. And the net ionic equation? Yeah. Okay. So the total ionic equation, how many potassiums did you get?
6.
This is soluble salt. And how many phosphates?
2.
Yeah, good. How many cobalts? Don't forget the charges on all these. And how many chlorides?
6.
How many potassiums?
6.
And 6 chlorides. And how many cobalt? Yeah, it just stays as solid. It's an insoluble salt, and so we don't touch it. Are there any spectators?
Yes.
Yeah. Looks like the potassium, nothing happened to that, and the chlorides, nothing happened to that. So all that reacted were the three, and you can write these in any order. I'm gonna write the cation first. 3 cobalts combined with 2 phosphates to make cobalt 2 phosphate. Cobalt 2 phosphate has this complicated formula, which is a precipitate. So that's what we end up with here. So I'll talk more about the other ones, the aqueous ammonia and some of these other ones later. It's just this, the supplement is emphasizing those, and so we'll deal with those a little bit later, and then we'll come back to the chapter, end of chapter problems here, which we'll take a look at next time. So we're not gonna start chapter 10 just quite yet.
This is chapter 9 though, right?
Yeah, this is chapter 9, and we're gonna do a little bit more 9, and then we'll go to 10.
So what was the total ionic equation?
B.